Doing, which is a little bit of a, a little bit of a handicap here in terms of putting together a lecture. And Keith appointed me to some of the lecture topics, which I looked at yesterday, and I realized that the one that I was listed under is not the top that I put together. So you'll have to bear with me. But one of the things that I did sort of think is that you guys probably have been, because of the cool field work that you did, probably been pretty focused on direct measurements of TKE in the vertical from shear microstructure profilers. And that is something that we do in our lab. I should introduce myself. Drew, professor here at Scripps. I have a joint appointment in the mechanical engineering department. And I'm the technical lead of the mod group right now. And we're a big group of engineers and academics, and many people are part of the group. And we provided some of the tools that you guys took to see last week. And, this kind of idea of measuring turbulence, or specifically the dissipation rate of KE from a vertically deployed microstructure profiler, provides some really important information about the statistics of turbulence in a particular time and place. But it is not the only thing that you need to kind of know when you are in the business of trying to make a budget for a tracer. And so we're going to walk through a little bit of tracer budget math. I put together like a tutorial, and I will send it around. It's still a little rough, so I'll send it around after the end of the lecture. I should have sent it beforehand, but again, still some time for me. But so we're going to walk through a little bit of a tracer budget kind of approach. And I'm going to hopefully convince you of, like, in the world of sort of tracers or BGC or whatever, that I'm going to try to give you some sort of like context and some caveats, because I do feel like, and I did a little bit of a literature survey, I do feel like when you look at turbulence and biogeochemical process in the observational literature, do see a lot of, diffusivity times a vertical gradient of something measured. And then that we call the total flux. And that's a really good thing to be able to do. It's definitely important, but I just want to show you kind of the full context. Okay, who's seen this equation before? Not the tracer specific one, but this word, yeah. It's the advection diffusion equation. It is the basics of a budget, changes some property in time, invective term. So it's a gradient of some property, then it's getting sloshed around by the currents. Over here, we have the diffusive side of the equation. So we have a diffusive coefficient, and then we've got some loss in it, second derivative of the distribution of the tracer. It's all written down here. And then, very unhelpfully, we have a problem when it comes to BGC process. We have this little S. And who knows what the S is? Who has so when I say BGC, I'm just talking about like basic biochemically mediated processes in the ocean. Who knows an example of one? Any sorry? Photosynthesis. Photosynthesis, sure. So photosynthesis is what? I don't need the kind of like stoichiometry, just in words.
Oh, like feeding food or fighting.
Yeah, okay, that's mentioned many of the important things. There's like, there's the sense of something being transformed, and the reality of that process is that it requires many things. We put a lot of them into a bucket that we call nutrients. That's what the N here stands for, maybe nitrate. And so that is a non-conservative process. What I mean by that is that relative to this budget, which we can constrain with physical measurements and maybe some measurements of the tracer of interest, the source and sink terms lead to a whole raft of things you need to consider. So first point that I'm making, this is a philosophical thought. You got to be really aware if you're going to be calculating budgets of stuff like nitrate or whatever, unless it's in a model where you're prescribing all of it, even so, probably hard. You need to understand that it can be very, very complicated And you really want to avail yourself of the fact that there are people that work in these fields very deeply and they know a ton about S that you know that don't, as a physical oceanographer, might not know anything about. I embarrassingly, I gave a talk in Santa Barbara a couple months ago, and I got these two words confused: nitrification and denitrification, in front of a bunch of biologists, and it was very, very embarrassing. So, I am still learning. So this is, we're just using N. So this is the nitrogen cycle in the ocean. It is very complicated. It has many, many, many different phases. It took people tons of time to figure all this out. It's really, really important, especially if you're doing a budget. It's really, really important to the BGC of the ocean. Not to go through all of it. I just want to point out one thing. The red arrows in this nitrogen cycle are kind of what the rest of our budget, the rest of our advection diffusion equation is. Okay, not all, but for example, this one here, this is nitrate. Nitrate is regenerated in the deep ocean below where the sunlight is. And it is typically limiting, or at least in some places in the world's ocean, that limits the amount of productivity. And so it needs to get from deep pool to shallow where it is needed for photosynthesis. Who has an example? Who has an example of what this red arrow might represent from a physical oceanographic? Upwelling, that's a great one. Upwelling is a type of advective transport, typically. I mean, it's not just that, but that's what it's most famously kind of appreciated as. What else? Right? An eddy, sure. That's another, some type of eddy stirring, tilted isopycnal. Okay. What else?
Sort of.
Yeah, any sort of mixing. Yeah, so kind of like I spent, at least kind of half my career working on this red line. Right. And I still don't know that much about it in some ways. And it is just one of the vast number of connections. This process here is the absorption of nitrate and organic nutrient into organic, and this is all of life in the sea. This little bucket, then it sinks. So that's sort of a physically mediated process, but also kind of just the fact that it gets exported. This is, by the way, like how this little guy here is how the ocean, the non-chemical part of the ocean regulates the climate and controls how much carbon dioxide is in the atmosphere. It's just this little back there. So I don't want to belabor it, but the point is that let us always remember when we're talking about the BGCs and we're talking about the fluxes and we're talking about using our microstructure profiler to go through here, get a turbulent diffusivity, divide it by the stratification, multiply it by gamma, get a diffusivity, and multiply it by the vertical gradient of nitrate, which is how nitrate flux is typically calculated if you're going to do it with mixing, either mixing and direct observations. That is just one part of this red line. And so when we're most interested is in budgets, and so we just need to be aware. Okay, speech over. Any questions? Okay, so this I'm mainly going to leave you with. I'm not going to, it's stupid to, I'm not going to write it on the board to just kind of talk through the derivation. But the first thing I want to say about the tracer budget is that I just highly recommend that you're always thinking isopycnal. There's a reason why there's isopycnal layer models, numerical models. And when we are making observations, to the extent that we can, and this is something that's not typically done by the biologists or chemists, I don't really quite understand why, but it behooves us to do so. So I'm not going to go through that part, but the key, wait, I will go, so here it is, so it's all the way at the bottom. This is exactly the same advection diffusion equation that we just saw in Cartesian coordinates. Now it's relative to isopycnals. There's some new things that we have to consider here, particularly this term here. This is this omega here is a diapycnal velocity. And so this kind of term, diapycnal velocity, is simply the material derivative of the density field in time. And that term there is a hard term, and one that, a hard term quantified. And one that, pretty much is only approachable through a Lagrangian approach, like using dye or maybe a Lagrangian flow. So we're gonna talk about ways to think about that one. And then here's the one I was referring to earlier. Now we've got our tracer gradient, relative to the density field. And the nice part about that is that we're kind of then allowed to use the diffusivity that we are actually getting from our profiler diffusivity dense. Okay, that tracer budget, the thing about isopycnal coordinates is that they, unlike Cartesian coordinates, is that the isopycnal coordinate system doesn't have to be uniform in space. And so what that means is that budget that I just showed you is actually non-conservative. Isopycnal layers can be different, different vertical spacing. They can, in time, change their relative positions to each other. They can have variability in space. And we're all very familiar with this by looking at maps of density, sections of density. And so there's another step that you have to do in order to make this a conservative equation, multiply by the layer thickness, and then integrate. Well, typically, that's what we do when we're actually going to end up with the budget. So here is, again, I'll send this around. This is just for your reference. But here this is exactly the same equation we just saw, except for just multiplying through by a layer thickness. So that's another thing to remember. And it's easy to forget that. I forget that a lot. You know, we shift things into isopycnal coordinates a lot. A lot of the technology that we build in our lab is like specifically so that we can be in isopycnal coordinates. So fast profiling systems, our wave powered profiling vehicles, your fishing rod reel that you use. The whole purpose of that type of system is to get time resolution with that density, with depth resolution of density, so that you can observe your quantities relative to the isopycnal. That greatly simplifies a lot of calculations because you can get rid of the vertical advection from internal layers. That's the very most zoomed out way. But when you change to those that coordinate system, you can fool yourself because the distribution of density is not uniform in depth, and you can create a situation where you have sort of a non-conservative perspective on things. Be careful of that. So you just need to remember that it's got to be layer, you know, by layer thickness. We're adding a length scale in order to make this into a budget. The question is, yeah. You go and settle the mark is like, so then like how do you or well, exactly. So it's a great question. So I'll try to go into a little bit more detail. So in this case, we're kind of assuming that we can get all the things that we need relative to isopycnals. So that is to say that, say we went out there with the ship and we were measuring the density field below us. We know the vertical distribution of density and its time and space variability. And then we're taking other measurements. So we're measuring, say, velocities, or we're measuring the concentration of the tracer. And the idea is that we want to know, like we're using the isopycnals as material surfaces, and we want to know the variability of those quantities on those surfaces. And so it's a mapping, because typically we have, say, for example, velocities from the ship. That's basically Cartesian in nature, like in the way it's collected. You beam out sound, and then it reflects off of some stuff in the water, comes back a certain time later. And that is naturally, the frame of reference is relative to the transducer at the hull of this ship. And then because it's timed, it's kind of equally spaced from there. So the goal is to take that kind of quantity, you know, there can be others, even your microstructure profiler drop down. Because you've got co-located information about the density field, then you can map your variables to density. So you're completely correct. What we're interested in here, this QH sub H here, is the velocity in an isopycnal coordinate system, meaning that the velocity along isopycnal, well, the horizontal velocity along isopycnal. That's actually the reason why this term is broken out. In the Cartesian budget, it's a, east-west velocity and north-south velocity and up-down velocity. These are horizontal along isopycnal velocities, and this is what the vertical velocity is. And it's actually the time rate of change, vertical density. Is that helpful?
I don't know if this makes sense, but what would be the difference in between isopycnal scales and Lagrange coordinates?
So they're related.
Yeah, they're related. but-
Exactly. And so like, if you are mapping in space, but relative to isopycnal, or able to transform your vertical coordinate to an isopycnal coordinate system, people sometimes refer to that as quasi-Lagrange. The reason why they refer to it as quasi-Lagrangian is because you are accommodating the fact that the vertical heat of isopycnals is accounted for. And so that doesn't map into the variability of the quantities. And it's a natural, the ocean operates this way. The ocean operates relative to isopycnals. So, the classic kind of, people say dipycnal mixing, dipycnal mixing, dipycnal mixing. We're kind of measuring mixing in the vertical, but what we're all interested in is things that are across isopycnals, and things that are along dipycnal lines. And again, this isn't kind of like, there are definitely like isopycnal layer models out there that have VGC modules. And so it isn't completely unheard of for the VGC people to do things on isopycnal coordinates, but that's forced from the PO side. And folks in the VGC world tend not to think of this from this perspective. Right. So let me just click through. Thank you for your very good questions. I'm like just writing this stuff down kind of like in the last like 16 hours. So I probably don't have it. There could be sign errors, and there could be all sorts of stuff in here. It's a work in progress. No, that's okay. So anyways, now we're kind of integrating over the layer. It doesn't matter the math, I'll send it around. We're kind of integrating over the layer, and there we are at the end, and I've kind of had it simplified a little bit. And now we have a bunch. So this is a conservative tracer equation. It's been integrated over the layer of interest. And now we have the ability to say kind of exactly what's going to be changing the quantities on within any particular isopycnal. Okay, so this is where I wanted to get to, why I wanted to kind of talk about this with you all. I need like a pointing.
Oh, there's one on that.
Yeah, that's. I like that. Now on to business. Okay, so this is again contextual. So you guys went out there with the fishing reel. You made the measurements of the turbulence, TKE. Well, you made the measurements of small scale velocity fluctuations, then fit canonicals back into in order to determine an energy level, which then gives you a what? What does it give you? What is the quantity that you are striving towards in your observations when you're processing your shear microstructure? Epsilon, right? Epsilon is what? Right? And what are the units of that? It's various, watts per kilogram. It's kind of the one that I mainly, use.
The wire, for some reason, comes off of that.
So it's no more equations. All right. Back on the demo. Okay, so you have TKE, which is nice. It's a nice quantity to have. But you're not really in this case, we're not concerned about the energetics of the ocean, we're concerned about the tracer budget. So what will we do next with our dissipation rates of epsilon? If we were to care about tracer budgets. Again? Exactly. So the next step, or the commonly used next step, is calculating diffusivity. It's pretty much always done, as far as I'm aware, in the BGC land. People fight about it all the time, obviously, but with what's known as the Osborne model or the Osborne-Fox model. And it's basically just a statement about the buoyancy flux. And that some proportion of the buoyancy flux goes to dissipation and some proportion of the buoyancy flux goes to mixing. That's the gamma. And so you end up with something that you guys have probably all seen. Looks like, maybe it's like Tapper Road, gamma, and then it's epsilon by like squared. And that's pretty nice also because you have n squared. Almost by definition, if you've collected your vertical profiles, you have the CPD, which you kind of have to have. You have your n squared, so then that's the capital. So that's this. And so what this term is saying in this budget is that the entire budget is saying that the only things that can change the mass of the quantity of the tracer within your layer is a divergence of a horizontal advection, a divergence of a horizontal diffusion process, and then things that are fluxing across the boundaries of the isopycnal. This is the diapycnal component here and here. So you're very happy, you have your microstructure, you have your kappa, maybe you've measured the tracer. That should be measured as a function of density. And then you can calculate with your kappa, what is kappa times the gradient at the bottom surface or whatever, rho one. The bottom of the layer, if you will, or the more dense or the more dense side of your layer. And then you have it at the less dense side of the layer. That's another important thing to remember is that this is also like a divergence, right? Because you kind of got, or you do have a top and a bottom of this layer. And so you have to keep track of not just what's fluxing up into the layer, but what's fluxing up out of the layer. And that is a divergence. Okay? So there's a key component. This is why we do this in a layered sense, is what we're trying to do is we're trying to constrain in any particular kind of density class, what's coming in and what's going out. So this is where you guys on the, if you have a tracer, this is where on shift you can calculate this. What I was hoping to do, and I didn't get through to, and I apologize for, but the next time I do this, I will, is a scaling analysis to tell you the magnitude of these terms. But what I know is that in a lot of contexts, if you scale these terms, this one is the smallest, or maybe this one. These two are the smallest. Yes.
What is the middle one?
This is the diapycnal velocity. So this is an advective term, but it's the advection of the nutrient tracer into the layer or out of the layer due to a diapycnal velocity. Diapycnal velocity is fluid following change in density in time. And again, this term here is kind of what dye studies are about. Or Lagrangian flows. Following a fluid parcel, in a Lagrangian sense, how does its density change? I have a hard time. There's some comments about diapycnal velocities. It is a hard concept. Okay, so when it comes to what we can do observationally, I would say, in sort of the state of the art, if we're doing not like a, sulfur, hexafluoride, deep ocean, completely inert tracer experiment, which people have done, and it's awesome. Instead, we're dealing with a reactive thing that's more relevant to like BGC. In terms of ocean observations, in terms of a layer of the ocean's layer, what can we measure and what's easy to measure, what's hard to measure, what we have good strength on, what we don't. Okay, typically we can measure the mass of the tracer within the isopycnal layers. That one's typically pretty good, and whether we can get a time derivative of it just depends on how much sampling we're doing. This advective term, this is the normal advective term, if you will. This is the long isopycnal gradients in your tracer multiplied by the long isopycnal horizontal velocities. That one also, you normally can get some information about. You have an ADCP on your ship, got a nice tracer resolved as a function of density in time, and you've got some shot at this one. This guy is the horizontal diffusive flux. We have scaling arguments that tell us it's something like 1,000 times bigger than the vertical diapycnal fluxes, but typically difficult to measure. Kind of the state of the art these days is measuring this. It also depends critically on the scales that you're interested in. So for some people, this might be small scale, like the sort of horizontal component of 3D isotopic turbulence. For other people, this might be more like a near inertial waves impact on the distribution of a tracer through something like shear dispersion. Right? But for somebody else, that might be advection. So this one here depends on the process and depends on the scale. And you really have to kind of be thinking critically about what you are after when you're doing your budget. What physics of the ocean. This is a fundamental problem of ocean budgets, is the multi-scale nature of the the non-linearities of the ocean. And then there's this guy, which again is all of biogeochemistry. It's like a quarter or a third of Scripps oceanography works on just this guy here. So this one is get your colleagues, talk to your friends, get the biologists on board, get the modelers, get the marine chemists. So this one you're gonna have to phone a friend. Okay. And then I don't know why it's not on here. And then there's this guy. And again, this one here, you guys just measured that when you were at sea. Actually, you measured this one. So you didn't measure nitrate, right? But you measured, say, sea level. So you measured this guy, you measured this guy, not this guy, and that guy. So pretty good. Pretty good. But remember, there are these other things. And really the only thing you can really do budgets, really with all these terms is kind of familiar. But we aim to please in operational community, and so we're working on these things. And getting, beating the error out of some of these terms. Okay. I will send this around once I've cleaned it up a little bit more. You can throw it in the trash, whatever you want to do. Just so you have it and benefit with it. And I just wanted to just bring a little bit more context to the really good work that you guys are doing in terms of learning how to think about turbulence at these small scales, isotropic turbulence from these observations. Okay, I'm going to change gears here a little bit. I'm going to continue to talk about mixing. I'm not going to have any microstructure observations in here, I'm sorry. But it is an alternate approach to understanding mixing in the ocean, especially when it comes to these BGC kind of things. And this is an in-progress study, which I think is pretty interesting, but I guess we'll see. Any last thoughts about the budgeting and yes. Wow, great question. That's an excellent question. Excellent question. Let me throw something back in. Okay. This is a vertical distribution of nitrate with depth in the North Pacific. Oh, sorry, North basins. This is from Sherbrooke's famous textbook that he wrote when he was here, of those things. And what is very true is if you go out to the Pacific right out here, and this is in depth, wasn't doing it in density coordinates yet, but you go out to the Pacific and you measure the distribution of nitrate with depth, you will get this curve. Okay, like this curve, pretty much exactly, you will get again, especially in the deep ocean. Why is that? What does that mean about the process? Slow, steady, exactly. It's a balance, basically functioning a balanced process that's in steady state. The supply of nitrate is balanced by its uptake into biology at large scales. And that's a very useful fact. It's a very, very, very fundamental fact about the ocean's couplings between physical domain and the biogeochemical domain. The reason why it's partially an answer to your question, Kaylee, is that processes that are in steady state have long timescales implicit in that S term. And when you have a long time scale implicit in that S term, hopefully you can kind of get rid of it and just focus on shorter time scale, if you're interested in shorter time scale processes, on the shorter time scales. It's not a great answer, but the point is that like some biogeochemical processes tend to, at least on large spatial scales, tend to have long time scales. Other stuff, not so much. What is this? Inorganic nutrients? There are organic nutrients that are produced in the like recycling of biological material, even in the mixed layer. And those compounds have really, really short lifespans in the mixed layer, like order minutes to hours. And in those cases, the budgets are basically dominated by the estimate. So, yes.
And related question, I was just thinking of like, in our FC, we measure both pi and epsilon. And I assume some of these variables might have a temperature dependence. Is that like thinking?
Yes. The deep, dark secret is that there's a ton of nonlinearity here. So this guy depends on temperature. This guy depends on this term, the rate of change, how much tracer is available is often an impact. So this whole thing is nonlinear and has, so the like BGC models and stuff have all sorts of kinetics. Michaelis Menten kinetics is the name for like the kind of rapidity in which an organism can uptake the tracer. Their respiration is temperature dependent. So yeah, so that's another problem, or another complication to the budget is that the kind of one of the terms of the budget depends on the time rate of change of the amount of quantities. So that's kind of why this is like all fine, but then you got this guy. Yeah. So yeah, great point, great point. But do not despair. I feel like I've been like, oh, it's so hard. It is hard, but you should not despair because it's really, really important to understand these budgets. This is like the currency of our climate. The oceans impact on. It's like figuring out how to get the tracer budgets right. It is a lot easier, and that's the reason why like Jim Ladwell or whatever uses, or any dye study uses an inert substance, because then this goes. And then you've just got this. And that makes life a lot more trackable. Okay, yes.
When you said that the vertical fluxes, the ones that I think are cool and interesting and trying to measure here, are the smallest, how much smaller is the smallest?
It just really depends, so this equation is, you really gotta make choices about scales when you employ the budget. And so like, if you're dealing on like, the coastal ocean scale here, or, order a few kilometers, it may be that the budget's very 1D. And like, just like in a key budget for the upper ocean or whatever, like there are times where you can say, okay, my budget's 1D. Like I don't have to worry so much about the effective terms. So you'd employ kind of a similar approach. The steady state nature of the distribution of the inorganic nutrient tracers does suggest that this is a very important term, as does the shape of the profile, which is what we call diffusive shape profile. If I'm remembering my intro level biological oceanography. So yeah, this can be a crucial component, but there's certainly circumstances in which these sort of horizontal terms And I'm gonna show you one right here in a second, where these horizontal currents are. Okay, wow, I talked so much. Wow. That's good. Okay, so just very quickly, you guys have been working over here somewhere. Um, thanks. We've had some moorings out up here, which is north of us here at Del Mar. And the moorings were out for a long time. This is kind of in the late fall, a little bit later than this time of year. This is a pretty typical sea surface temperature, sea surface chlorophyll, pretty typical for around here. I wrote in my thesis dissertation papers on this. I called it in the title of the paper, the green ribbon, made it red here, not the land, but it's a narrow band of high chlorophyll water that's associated with slightly cooler water near the coast. It's kind of like an upwelling-ish sick. Don't want to get too much into the semantics of what is and isn't up. So this is typical, probably what's happening right out offshore right this instant. During the winter months here, or the transition to the winter season, we get the passage of low pressure systems. Low pressure systems come with south winds from the south and from the southeast. Those winds are downwelling favorable, and they create a response which is seen here and here. So there was a passage of a pair of low pressure systems. After their passage, we ended up with this situation. There's been downwelling, so this warm water has moved onshore. Their full band of water, nearshore water is gone. The chlorophyll signal is much reduced and pressed all the way up against the coast. So the water nearby the coast has become, this is a winter storm, has become warmer and clearer. That's already kind of interesting. So here's our isothermal coordinate system coming up. This is what a traditional mooring looks like. You have fixed sensors. This is what a profiling mooring buys you. These are shown with the same, these are right next to each other. Basically. And these gray bars are the isopycnals that I'm talking about. This is the internal tide. And then we had a mooring, but these weren't next to each other, excuse me. Down one moorings at 100 meters of water. This wire walkers, we had two experimental setups. This is the second. The wire walkers in 50, and then we had a mini mooring in 20 meters of water. Then here's this nitrate quantity. So in this case, I had a nitrate sensor on my moored profiler. And so here I have full depth, tracer, resolution, full depth, distribution of tracer with the time result isopycnals concurrent. So this I can turn into isopycnal coordinates. And I've got roughly like every 5 minutes, I have a vertical profile over the course of weeks. So I have excellent time. Okay. And what we had noticed, it was very, very strange to us. Here's the downwelling event. So here comes, water's kind of cool, mid shelf, kind of cool, winds kicked in, becomes this blob of warm water. And we're still in depth coordinate system here, but if you take your tracer and you calculate an anomaly by just taking sort of like what it was at the beginning and kind of subtracting that off, what we find here is this weird anomaly where the nitrate is higher in these depth ranges, and as we will soon see on these isopycnals after the downwelling. So there's a very odd thing, and most people in the biological oceanography world think of downwelling as being anti-production, anti-nutrient fluxes. But so here we were very puzzled. Here's a little bit of an understanding of the velocity fields out here in Southern California, extremely internal wave dominated, or directly forced by the wind, high mode content, lots of vertical variability, lots of time variability. Cross-shore velocities, long-shore velocities, there's no filtering in this. This is just how they come out of the ADCP. You see these, generally southward or longshore flow to the surface, generally northward. So playward flow to the surface, forward flow at depth. This is the normal condition. And then that relaxes after the onset of the downwelling favorable winds. Okay, so really, these are the wind stress. Yeah, wind stress. The other thing about these winds is they tend to rotate strongly over the course of a day, basically an inertial period. So they're not only downwind favorable, but they also like to kick off big near inertial oscillations. That's what you see here, strong. We're slightly subinertial here with diurnal forcing, but it's like directly forced. This isn't like a propagating wave. This is like imprinted on by the wind, the phase of the world. Please. No filter. 100% how they come out of the east. Very strong signal. Very strong signal.
Would
Yes.
you mind resharing your screen? I think it's zoomed in really weirdly on.
Okay.
Just I think if you do escape from this.
Escape. Stop share. Oh boy, now I got two desktops going.
Sorry. I think if you just share your desktop.
See here. Think my mirror? Yeah, I am mirrored. Where did my? Okay. Oh.
Thank you.
Okay.
Yeah, that's good. Thank you.
Okay. So now we're in isopycnal frame of reference. So this is just time series plot. I picked that isopycnal where that red with red blobs were. I think it's the layer. So again, we're doing this layer integration. I think it's the layer. Oh, maybe. This is gonna screw up the Zoom again though. That's what happened last time, the plug is unplugged. Oh no.
And it's back to being the sphere version, but I feel like if you slide your screen,
Slide my screen?
no, it's fine. I think you can see it on the screen on your.
Try one more time.
Okay. Oh, that one. I think Google Chrome up there.
Here it is.
Ah. Yeah.
Okay. So it's these layers, it's the average of the tracer quantity in between these two isopycnals here. So this was the second puzzle. This is just a time series. Now we're looking across the shelf. And the profiling mooring here is in black. You can see we have full time coverage because we can track the isopycnal and at all times, because we're covering full ocean depth, full depth at the mid shelf, and we have good time resolution. So the first thing that jumps out, this is on the isopycnal now. So we expect that this to be that you know, in general, we expected nitrate and isopycnals like pretty conservative. Instead, the very first thing we see is on this isopycnal, huge variability in time. But that was surprising. And the second thing we saw is that red is inshore and the cyan color is offshore. The next thing we notice is that once this, you start seeing this isopycnal inshore, it's kind of in the middle of the water column. It had higher nitrate on that isopycnal than the values offshore. So this was also puzzling. This means that these offshore waters cannot be the source of this nitrate, at least in a horizontal advection situation. And so all of a sudden, we've kind of discovered two important things. One is that there is clearly a long isopycnal gradient of the tracer. And that long isopycnal gradient is directed from a higher concentration onshore to a lower concentration offshore on the isopycnal. Very weird. So what time scale is this? Well, these are these near inertial waves, just diurnal. It's a forced diurnal wave. You see it, they're really focused in these middle depths, and that is the time scale. So what we're seeing, you know, we're using the fact that the near inertial waves are moving the water back and forth in order to measure the gradient on the isothermal. So it's an oscillatory flow. I'm not talking about anything to do with mixing or shear dispersion. Just saying it is sloshing back and forth by the mooring. We know how fast it's sloshing back and forth by the mooring, know how long it's taking. So thus we have a length scale. We know the change in concentration. And we have a length scale, we have a gradient scale, and thus we have a long isothermal gradient estimate. So we can do a little trick when you have stuff that's sloshing back and forth, is you can turn your mooring into a virtual ship section. Right? So the ship drives through the water, and you collect your data and you get a section. Or you can stand there and let the water move past you. It's not as good as the ship because things can change because it takes a long time for the water to move past you, but you can do something like that. And so here we've, just as I said, we've reconstructed, this is isopycnal coordinate system. This is cross shore distance. Using that advection, we're able to create a section. This is like a pseudo cross shore section of the tracer in isopycnal space, which shows that the nitrate increases on isopycnals as you move inshore. So that was pretty fun. We can do that for all sorts of different variables, and we can do it both before and after the downwelling. So here are, they're all just sections like I just showed you. This is nitrate, nitrate anomaly now. This is before, this is after. Water was fresh and cold. Near the surface, it was very green, it had a higher amount of backscatter. Then the downwelling moved in, then no, the on isopycnal nitrate was the same no matter where you were in the offshore. Then the downwelling happened, all of a sudden we got this major nitrate gradient on isopycnals. The water has become saltier and warmer near the surface, and the chlorophyll is disappeared from the surface and now it's at the subsurface maximum. And very tellingly, there is optical backscatter that is also now distributed at depth, and it also has a cross shore gradient where it's higher onshore and lower offshore. Who knows what that might be? Go ahead. Yeah, this is a daily oscillation. So this is calculated as average, the canonical average of particular 24 of consecutive 24-hour period. So we make a map for a day and then we average a few of those days together. Then we have before and after. I worked on this with my graduate student, both, and we put this together. Okay, so another very useful way of studying tracers is the good old TS diagram. This is a TS diagram, except now because we have this additional component, which I am treating, little dirty secret, I'm treating S as 0. Right? And I'm saying that now it's a 3D TS diagram, and I'm kind of imposing, not true, but I'm imposing that nitrate is also conservable. That gives us another dimension, makes our TS diagram even more powerful. And you can see that there's sort of the before case called upwelling, and after case, you can see there's been a change in the TS properties associated with the increase in the nitrate. So an isopycnal, this is an isopycnal, anything in the parallel like this isopycnal. Here it's low, and here the nitrate is high on those isopycnals. So the beauty of a TS diagram is once you have that, you know that mixing in a TS diagram happens on straight lines between points. So this is a recipe for understanding mixing that in some ways is much more integrated, doesn't tell you the process, but it has the result of all those terms in your budget baked into it. So in a way, it's a direct measure. And what it shows is that there's, well, if you just kind of say, okay, we've got this subthermocline water, we've got this water above the thermocline, then we have this intermediate water in the thermocline. And it started off kind of like this, ended up kind of like this. The only way to get water of this character outside of it just evacuating from somewhere else, is the mixing between these two. In fact, these values lie, the TS values lie directly on the mixing line between the above thermocline and subthermocline waters. And as I told you, we had another tracer, we have nitrate. Nitrate's close to zero here, and it's got some value there. If we have an admixture of those two different water masses, we can make a prediction for how much nitrate it should have, assuming it's conservative. And then we can use our TS to predict the nitrate and then compare it against the nitrate concentrations that we found. And we find a very good. So basically what I'm saying here is that the TS diagram tells us that this water D that wasn't there before is a mixture of B and A. And the D shows up when we see the high nitrate anomaly. And that creates, this is a nitrate concentration versus temperature, which is a way that people look at it. That creates an excess of nitrate in this temperature and salinity class that wasn't there before, because this water is newly ventilated. It's a newly created mixture of surface and subsurface. It has not yet had the nitrate taken out of it by non-conservative processes. And this is a very famous animation that I'm sure many of you have seen before of a tracer on a slope. Here you've got boundary mixing associated with internal waves. Great Winters, super famous. The experiment that Matt and Alfred led, that Beckman did their PhD on, called PLT, was directly studying this process. Put dye in the bottom boundary layer, watch it spread offshore. It's mixed in the bottom boundary layer, creates an on-isopycnal gradient, and then it's stirred into the interior on isopycnals. We believe that's exactly what's happening here with our nitrate. There's mixing happening. The downwelling pushed the warm water from the surface into the cold water from below into close proximity with each other into the bottom boundary layer. There's some unknown energized bottom boundary layer mixing, probably has to do with the internal wave sloshing. And the result is that this creates water of this density class that has higher nitrate than the canonical situation or the previous situation as well. And so that boundary mixing could then be a source of new nutrients, but during downwelling.
When you're talking about this, like with the weather event, and you're just near the surface, does it make sense to treat the temperature as conservative? Because like if the surface heated a bunch, all the isopycnals would shift down. If that was the only thing changing, it would look like a really high nitrated anomaly. And it might look like this, but I just don't know.
Good, that's a good question. I've ruled out surface fluxes here. I didn't even talk about them. They could have an impact. I guess what I would say is that the magnitude of heat flux necessary to go from this condition, this is warming associated with the warm front coming on shore, is way more than there is available. This is warming up by several degrees C over 10 years flat, nearly instantaneously. So that is advection. But it's a very good point, which is that when you're dealing in isopycnal coordinate systems, you do need to be careful of the, other types of forcing that can change the density of with diabatic processes.
I'm saying so because in order for this signal to exist in it, like that has a good phenomenon. You don't need the temperature to cause the full like ice. You only need that to cause enough isopycnal movements to change nitrate over the period, over the like steep fall off the nitrate. So you don't need that all to get explained by temperature for this, just like electricity. Okay.
Maybe, I don't know that I can completely understand. What I would say is that the kind of other piece of evidence here is that we're seeing these anomalies, this anomaly to be appear Yeah, I mean, I guess. I have to think about that one a little bit. Like, basically, our main lines of evidence are that we have a clear. Isopycnol signal of nitrate variability in the cross short. See it going back and forth over the course of the day. Completely phase locked with the velocity, so we know it's affected by us. We know it's higher inshore than offshore on that isopycnol, and we know that the TS nitrate characteristics are consistent with it being a combination of surface water and subsurface water. So those are all good strong pieces of evidence. Whether I could rule out whether there could be a cross-shore gradient in the heating on that isopycnol surface, which may be shallower inshore than offshore, I do not know that I can rule out. I'm saying there before you, but I will get that. Okay, I've gone over time. Appreciate your time. Any other questions? Please fire away. And yeah, I hope that was probably a little bit different than what you kind of expected, but hopefully that was somewhat useful. Thanks.